So I'm presenting the paper using program analysis to identify the use of vulnerable functions. It's written by myself, Rasmus Hagberg, as well as Martin Hell and Christoph Reichenbach. It's written as a collaboration between the computer science and the electrical and information technology departments at Lund University, as well as with the SECRYPT, which is a cybersecurity startup based in Malmö, Sweden. So for this presentation, I'll start off with a bit of background and motivation as to why this is an important problem. I'll then give an overview of the theoretical framework that we have created. I'll then move on to our implementation of this framework in the Java language and the Maven dependency management framework. I'll then talk about the results that we get when using this, as well as some problems and potentials for improvement, and finish off with the conclusions. So for a bit of background, open source is absolutely everywhere and it's great. It allows you to save time. It makes it so you don't have to reinvent the wheel each time you make a new project. According to Synopsys, 99% of the projects they audited used some sort of open source. And on average, 70% of the code base consisted of open source, meaning there is more open source in an average project than there is purpose written code. But of course, importing code means importing bugs. And when there's a lot of open source and a lot of published vulnerabilities, this can be very hard to keep track of. What's more, you need to know not only if you are using a library with a vulnerability, but if you are affected by the vulnerability in question, because otherwise it's fine. You don't have to update, which you might want to avoid for various reasons. This analysis, however, is time consuming, it's error prone, and most of all, it's hard. So we would like to automate this. Unfortunately, that's also quite hard, mostly because the data is formatted by and for humans, making it very difficult for machines to read this. But doing so would save a lot of time. And so that's what we do in this paper. We present a tool with an implementation for Java and Maven that on average removes 20% of all vulnerabilities by concluding that the vulnerable functionality is not used. We want to automate as much as possible of this process so that we can, for example, include it in a CI pipeline in the future. So now I'll explain the framework. So in order to figure out if you're affected by a vulnerability, you as a developer need to answer 4 different questions. First of all, you need to know what libraries you're using. Secondly, you need to know which of these are actually vulnerable. Thirdly, you need to know which part of the library is vulnerable in order to finally figure out if you are using those specific parts. Like I said, this takes a lot of time and effort, and it's hard. You need to know a lot about the program you're analyzing. The picture you see on the right is an illustration of how our framework works. It's quite a lot of data, but you don't need to understand it all right away because I'll be going through it step by step. So let's start with the first questions. What libraries do we use? For Maven, these projects define their dependencies in a pom.xml file. But we are not only interested in these dependencies, but also in the dependencies of these dependencies in turn. Even if you have only a few dependencies, these dependencies often have dependencies in turn and so on. And we need to know all of these. Fortunately for us, Maven has a built-in command to easily list this. The output you can see at the bottom, where we use the Mockito project, which in turn has a bunch of other dependencies. So this is great for us. This allows us to very easily answer the question. Unfortunately, the next few questions aren't going to be quite as easy to answer. So how do you tell if the libraries that you're using are vulnerable? Well, you will need to consult some sort of vulnerability database. And vulnerabilities live in many places. They live in GitHub issues, they live in security advisories, mailing lists, IRC logs, you name it. But the source that we focus on is NVD, which is a large centralized database of vulnerabilities. It has over 150,000 of them. And so we choose to use this as our source. They enumerate their vulnerabilities using CVEs, which I'm sure you're familiar with. Essentially, it's just a way to to name a vulnerability so that you can refer to it easily. When listing what is affected by a vulnerability, they use what's called CPEs, which is also essentially just a way to name a library, a version of a library, in order to attempt to have a standardized name for it. The CPE field has 3 interesting fields that we care about, which is the first one here, netty, which is the vendor. The second netty is the product, and then the version field. Maven defines their libraries very similarly. They have a group ID field, which is the group that makes it, an artifact ID field, which is the name of the artifact or the library, and then finally a version field. So while one might initially think that this is great, this aligns perfectly, unfortunately, it doesn't always do so in practice. As you can see in this example, this is in fact the same library, but in fact, all 3 fields differ in some way. So in order to properly detect this, you need to figure out a way to overcome this issue. But once you have done so, you have successfully answered the second question. For the third question, we can once again consult the vulnerability databases such as NVD. Because these have information about the CVEs, unfortunately, this information is very much intended for humans. This italic text is the description for the CVE from the previous text, previous page. And we can see that it mentions a file called HTTP object decoder, something about the content length header. So we can tell that this has to do with reading HTTP requests and handling them. This is easy for a human to tell. It's not that easy for a computer to tell. So we don't actually read this information at all. Instead, what we do is we read the information about which versions are affected. This is almost always available in these databases because you need to know which version is safe. So if we know that version X is affected by a vulnerability and version X plus 1 is not, then whatever changed in upgrading this version fixed the vulnerability, and so the vulnerability is contained within this set of changes. So what we do is we produce a diff, we translate that diff into a set of Java classes and methods, and then we store this away as the vulnerable functions, because changing these fix the vulnerability. Now, you don't always release a new version just to fix a vulnerability. Often you, for example, fix a bug or introduce a new feature. And in this case, we will unfortunately mark these as being related to the vulnerability as well, since we can't tell why a file was changed. We just know that changing it fixed the vulnerability. So we will introduce some false positives in this step. So now we know which parts are vulnerable. Now we need to figure out if we are using them. And the way we do this is we link the program we're analyzing together with the libraries, and we compute a call graph. We then look through this call graph and we get a list of all the functions that we call from a library, and then we can just check to see if this list contains the vulnerable functions. If it does, we know that it's possible for you to use these functions that are associated with the vulnerability, and so we say you are vulnerable. If the list does not contain this, then you are not using the part of the library associated with the vulnerability, and so you're safe. You don't have to upgrade since you're not using that part. However, constructing call graphs is a tricky problem, especially for modern languages like Java, which have a lot of features that complicate this. And this means that call graphs are neither sound nor accurate, which means that they have both extra edges that don't exist in reality, and they will miss some edges that do exist in reality, at least potentially. This introduces some false positives and some false negatives, which means we can never be 100% safe that you are in fact vulnerable if we see it, and vice versa. But it's a strong indication. We produce our call graph using static analysis. That is to say, we compile the program, but we do not run it. We could use dynamic analysis instead by running the program. But that means we need a suite to run it over. For example, the tests. However, we found that when tests exist at all for our dataset, they don't have that great coverage. When there even were tests, the average test coverage was 25%, meaning you will have a lot of missing edges. Now, for a higher quality open source project or an enterprise project or a project where you know you have a good test suite or other suite to run on, dynamic analysis could be a lot more viable. But for our use case, it didn't really work well, and that's why we went with static analysis. Of course, you could combine these, either looking at the intersection or the combination of the call graphs, which would have consequences for precision and recall, respectively. But in our case, we just used the static analysis since that fit better. So what are the results? In order to figure out the results, we looked at 200 random Maven projects from GitHub. We fetched them by sorting by the time GitHub indexed the project, which isn't truly random, but it's random enough for our purposes. Of these, 130 of them were useful. That is to say, they could compile, and they had working configs. There were a few as well that we had to remove because they had no code at all. But 130 good ones. And of these, we could analyze 114. The reason that a few fell away was because they used newer features that Suit, which we used to build the call graphs, do not support yet. Since we did this analysis, a new version of Suit has been released that does support more features. So this number would likely be higher if we were to do the analysis again. Now, of these 114 projects, 90% of them used some amount of vulnerable dependencies. This is a very large number, but since a few of the projects were a bit out of date, it's not necessarily representative of more up-to-date maintained projects. But still, it's an intriguing number. Now, of all these vulnerabilities, we were unfortunately unable to analyze about 20% of them for various reasons. All dependencies are not the same, however, as you can see in the first table in the top right. PostgreSQL alone is responsible for a third of the usages that we could not analyze. And this is because they do not post all of their versions to Maven. So when our vulnerability database says that this was fixed between versions X and Y, if version X doesn't exist in Maven, we can't download it and we can't analyze it. So we can't do our analysis at all. If we were to write a specific solution to this for PostgreSQL, maybe fetching the versions from elsewhere, we could thus reduce this amount by a third already. But this doesn't really scale well, especially not if you want to keep it 100% automated, which we do. In this second table that lists why we could not analyze some vulnerabilities, you see that this version not being available is in fact the most common reason. Another common reason is versioning scheme mismatch, where the version does exist in Maven, but under a different name. Maybe the Maven name has the release date or something like this. This causes us to also miss out on being able to analyze. There are a few other reasons as well. Sometimes the group ID changes, so the dependency changes namespace and we are unable to follow it. There are a few cases where there is no fix available. Obviously, we can't do the analysis then. But most of these cases could be fixed, which would improve the results. Now, for the most interesting slide of all, what are the results when we are able to analyze? We find that for a given project, 20%, or a given vulnerability rather, 20% of the time, the vulnerable code was found not to be used. This means that it's safe to continue using the vulnerable version since you're not using the vulnerable part of the version. Now, instantly removing 20% of all vulnerabilities would greatly reduce the burden on security teams everywhere. But there's potential to improve it even more. If we were to fix the problems on the last slide, we would go closer to removing 25% of vulnerabilities, but we can do even better than that. For example, as I mentioned when we were determining what part of a library was vulnerable, if we were comparing versions, so a version X, which is vulnerable, and the fixed version X+1. But if we could figure out, for example, a commit that fixes a vulnerability, we could compute the set of vulnerable functions over this commit instead of over two released versions, which would lead to a way smaller set of vulnerable functions. This would reduce the amount of times that we mark a project as vulnerable when it was simply using code that was bug fixed in this release that also fixed an unrelated vulnerability. This does run the risk of introducing some false negatives though, since you could, for example, pick the wrong commit. Now, finally, let me say a word on scaling. The library analysis part, that is to say, figuring out what part is vulnerable, can be reused between projects. You only need to do this once per library and vulnerability. This is obviously great for scaling since you can then use this data to analyze however many projects you want. The call graph construction was by far the most time-consuming part of this analysis, but fortunately it scales linearly with the amount of edges in the call graph. This means that as the size of the program increases, the execution time will increase linearly, which means we can analyze also very big projects, which is great. So to conclude, we have created a program that automatically detects if the vulnerable part of a dependency is used. We do this by determining first what part of a dependency is vulnerable, and then we use static analysis to determine if a given program uses those parts of the dependency. This results in a 20% reduction in positives right away, with room for future improvement. This will help security teams triage their efforts, allowing them to focus first on vulnerabilities where we can show that there is potential for exploitation, and upgrade other libraries later when they have fixed the most crucial ones first. And with that, I will conclude this presentation. Thanks for your time.